Hi there, welcome back. This is lecture 2, the Perceptron. So the goal today is to derive the Perceptron learning model, which is perhaps the simplest learning model that you could think of. Okay, so we'll derive it, but don't underestimate it. Even though it's a simple learning model, it's very powerful. And in fact, I'm willing to go so far as to say that you can pretty much solve any problem with the Perceptron. Mathematically, that is definitely true. And even in practice, I would claim that if you are having a very hard time solving a problem with the Perceptron, something is going wrong somewhere else. Okay, so we will develop this very simple but very powerful model, the Perceptron. Okay, and then we will pause, and I will sort of specifically address the type of learning we are talking about in this class, which is called supervised learning, in contrast to other types, other views of learning, both highlighting the similarities and the differences. Okay, so learning is a very broad premise, and it has been invented and reinvented multiple times, and in some cases those multiple times have resulted in separate disciplines. Okay, so machine learning is actually going on all over the place, and so it's a useful exercise to sort of see what's going on and how does it relate to what we're doing. Okay, we'll end with a puzzle, so stay tuned. Before we derive the Perceptron, let me just recap where we were from the last lecture. So we talked about the storyline, what is learning, can we do it, how do we do it, how do we do it well, and then let's step back in our storyline and talk about general principles, and lastly we'll add a few bells and whistles with advanced techniques, and we might mention other paradigms. Okay, so that's the plan. Okay. And we introduced the key players, and specifically in the context of this concrete example of credit approval. So, in the machine learning problem, there's an input X. Think of the applicant who applies for credit, and what are the properties, the attributes that the applicant has listed on the application. So salary, debt, years in residence, etc. We call this the input X. The decision that the bank makes, approve or not, yes or no, we call the output Y, and in this particular case we can encode the output by plus or minus 1. Plus 1 approve credit, minus 1 reject for credit. Okay, and this particular type of output is called classification, and this is what we will mainly focus on, although we will touch on when the output can be more than just plus or minus 1. Maybe it can be, let's say, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 digits, so 10 possible outputs. Could be a credit level, in which case it's a real number. Okay, so the output can take many forms. A very popular form is classification. Okay. Now, important, there is some pattern. There's some true relationship that maps X to Y. We call this the target function F. Okay, and that maps X to Y. F, the target function, is unknown, and we mean unknown. Well, it's not totally unknown, because then we're done. There's nothing to do. So in order to learn F, which is the goal of learning, we're given a data set. And in the case of a bank, the bank has data on customers, and what that means is that they have many applications from which they can extract X for each application, the input. Okay, and we assume that whoever's giving you the data can also extract Y, which is assumed to be F of X. So the data set is x1, y1, x2, y2, and so on up to xn, yn. Okay, where we assume that each y in the data set is obtained by applying f to the corresponding x in the data sets. Okay, now how this data set is obtained for the moment is not our primary concern, but it can, in several applications, be a challenging task, especially once we cover the theory and we see what constraints, what are the requirements of this data set deep. Okay? And usually, when machine learning is failing, it's because whoever gave you the data set failed to obey those constraints that are required by the theory. Okay? So it's important to understand the theory for at least one very simple reason, which is that the theory sets the rules for how you can collect a data set. And if you collect it according to what the theory says you should do, then everything else rolls on. If you don't, trouble. Okay? But for the moment, we're not addressing explicitly how does the person who's giving you the data, in this case the bank, how does the bank arrange it so that they can obtain Y by applying f to x when f is not known. So they have to do it in some indirect way. Now, in the case of a bank, we can easily imagine that what the bank does is it gets the applicants who, and checks whether or not after you lent them some money, they paid it back or defaulted. If they paid it back, f is +1. If they didn't, f is -1. Okay. So the input space, the nature of the decision, and the data set are given. Nothing you can do about it. Those set the parameters of the learning problem. The target function f is also in some sense given. It's fixed, but it is unknown. Okay? And the goal is that we have to sort of learn, we have to reverse engineer the target function f from the data d. Okay, so that's the setup of the machine learning problem, and we summarize that in a flowchart. Okay, in terms of step by step, how can we view the entire machine learning process from start to finish? Okay, so the whole process starts with an unknown target function, f. Okay, this unknown target function. So, for example, it's the ideal credit formula in the credit approval. This ideal target function is used to generate the data set. Okay, so you get x1, y1, x2, y2, and so on, xn, yn, using the target function f. Okay, now, you don't know the target function f, so that's where the trick is. You have to somehow indirectly have access to these y's. Okay. In the case of the credit approval application, these are the historical records of existing credit customers. Okay, they are extracted from the historical records. And the goal is a final hypothesis G which approximates f. And so that's the goal. That's the outcome of learning. And if you can output a G that approximates f, I don't care how you did it. Even if you didn't use data, I would say that you have learned. Okay, but when you do use data, we say that you have learned from data. Okay, so the goal here is that you're going to output a final hypothesis G which approximates f, in which case we say that you have learned. Okay, and you are allowed to use the data to output this G. Okay, now we restricted ourselves to a particular mechanism by which you produce this G. And even though I said restricted ourselves, it's essentially without loss of generality. Okay, so where's the restriction? The restriction is that before you see the data, and this is very important, it looks like a restriction, okay, but in the end it turns out to be without loss of generality. Before you see the data, you must fix a hypothesis set H. Set of hypotheses, a set of candidate formulas for credit approval. Okay, and then you say, oh, that's very hard to do if I'm not allowed to know anything about f, I don't know f, and I haven't seen the data. Well, in that case, it looks like a restriction, but if you feel like it's set H to be every function in the world, okay, and then you will not be faced with any restriction here. Okay, but allowing this possibility that you have fixed a hypothesis set H ahead of time, before looking at the data, will make the theory flow. And because that same theory applies no matter what you fix the H to, you can fix it to all hypotheses if you want, so it's still completely general. So fix a hypothesis H, okay, and now you are restricting yourself to, when you see the data, only be allowed to pick a hypothesis from H. Okay, so the game we are setting up, so the learning setup is that you're not allowed to then, after you look at the data, say, I'd like to change my hypothesis set. I'd like to change my set of candidate formulas. Not allowed. Okay. So bear that in mind when you fix the hypothesis set H. Okay. So fix it to something which you are comfortable with. It could be the whole universe of hypotheses, but whatever it is, fix it to something you're comfortable with. Now you get to see the data, and then your learning algorithm is going to pick a hypothesis from this hypothesis set, okay, and output it as the final hypothesis G, and then we will say that you learn if G is approximately equal to F. Okay. Let me sort of talk about three things here. So, first, how does the learning algorithm pick a hypothesis from the hypothesis set? So at a very high level, there's a whole bunch of hypotheses in the hypothesis set that are available to the algorithm. And now the algorithm gets to see the training examples, and it needs to pick one. So in some sense, we have to define some criteria by which it should pick one of those hypotheses. And let me give you some example criteria. Just pick one of those hypotheses randomly. Doesn't sound like a good idea. Where's the learning there? Just pick the first hypothesis. Also doesn't sound like a good idea. Pick a hypothesis that somehow depends on the data set that you now got to look at. That seems like a reasonable approach, but then that somehow is very confusing. How exactly? Okay. So one of the steps in specifying the learning algorithm is to identify what the criterion is that the learning algorithm is using to pick a hypothesis. Okay. So that's one thing that the learning algorithm has to do. And then and it should always bear in mind that the goal is to output a final hypothesis that approximates F, which is a test that you're going to face that is not going to be coming from the data. It's coming from some random other test example. Okay. The second thing that the learning algorithm has to do is it has to actually go and physically perform that task of picking. So there's a criterion that it's going to use in order to pick, but then it needs to go and implement that criterion and pick the hypothesis that's, let's say, best according to that criterion. So that's an algorithmic issue. So there's both the mathematical / learning issue of what's the criterion that the algorithm should use to pick a hypothesis. And then there's the algorithmic computational issue of, okay, how does the algorithm actually now go and search through this hypothesis set, okay, in order to find the hypothesis that satisfies this criterion. Okay, so there's two separate issues here. What's the right criterion, and how do you go and find it? Okay, and in general, okay, we call the algorithm and the hypothesis set the learning model. And in general, when you specify a learning model, you specify this hypothesis set, you must also specify the criterion, and you must also specify the algorithm, because there's no point just telling me, how you should pick it, what the criterion is by which you should pick a hypothesis without also telling me how exactly I should go ahead and do it, how exactly I should go ahead and implement that algorithm. Okay. And then lastly, the algorithm should only care about whether it outputs a hypothesis that's approximately equal to F. And I cannot overstress the importance of that criteria. And let me give you an example. So Edward Jenner. He's the guy who we consider to be the father of the smallpox vaccine. So now, in this whole COVID time, vaccination and so on and so forth is a hot topic. So let me tell you a little bit about how Edward Jenner and then how Edward Jenner and his actions ultimately led to, a smallpox vaccine and then the eradication of smallpox. It's an interesting story, okay? And it is intimately related with this, when I output a final hypothesis, it must be the case that this final hypothesis approximates F. Okay, not the data. Okay, so here's Edward Jenner's story. So around about Edward Jenner's time, so smallpox was raging, but it was sort of well known that milkmaids, so people who would be milking the cows, were sort of immune to smallpox. Okay, and it was conjectured that this is because somehow it was related to the fact that they had cowpox. So cows also had a version of smallpox, which was called cowpox, and then the milkmaids would sort of get cowpox, but this was not a very virulent form of the disease, and so they were able to fight it, and then in fighting it build antibodies for cowpox, but those antibodies helped them to fight smallpox, and so in the event that if they were getting infected by smallpox, they would have immunity. Okay. Now, that's sort of what we know today, but at that time, all that was known was that, milkmaids were immune to smallpox, and somehow it was conjectured by people even before Jenner that, it might be related to the fact that they're around cowpox. That's the data. So in walks Jenner and looks at this data that milkmaids are immune to cowpox and says, well, I'm gonna have a hypothesis. I'm gonna have a hypothesis that if I inject you with cowpox and you survive, then you become immune to smallpox. So that's equivalent to the hypothesis, G here. That's Edward Jenner's hypothesis, which he has learned from the data. So it's an interesting example of real life learning from data. Okay. And how is he going to, convince people that his hypothesis is true? So here's what Edward Jenner did. Okay, so he went to milkmaids who had cowpox, and you have the pox, and inside the pox is pus. This is kind of a gross story, and he pulled pus out. Okay, and his hypothesis was basically that this pus contains cowpox, and so I'm going to inject pus into you, this cowpox pus into you, and then somehow miraculously you're going to get immune to smallpox. Well, this is a very far-fetched story, and it's an interesting hypothesis, G, and it might explain the data, i.e. why the milkmaids were immune to smallpox, but was it really true? Was it really going to approximate a true immunity to smallpox, i.e. would it give immunity to a random new test point? Okay. So how could he test this? So he needed to test this hypothesis, this final hypothesis of his, and so he needed a poor soul who was willing to subject themselves to this test. So he went to his gardener and he said, you know what, I'm going to inject your son with cowpox, and then I'm going to inject your son with smallpox, and then we're going to see if your son gets sick. Now, put this in context. Everyone around these people are dying from smallpox, and he's proposing to his gardener that he's going to inject the gardener's son with cowpox. Okay, well, the gardener doesn't expect the son to die from cowpox, but then after injecting the son with cowpox and waiting for a couple of weeks or whatever till he recovers and gets immunity, he's then going to inject him with smallpox to test and see if the virus works. Okay, so that's the story of Edward Jenner, and you can imagine he must have had a very faithful gardener who really trusted in Edward Jenner, because the gardener said, yes, sure, go ahead, do it, boom. And lo and behold, the son was immune to smallpox, and blah, blah, blah. Smallpox vaccine gets invented, and smallpox gets eradicated. Okay. That is just, to show you that this criterion that the final hypothesis must approximate F, and we don't care how it looks like on the data, is a very, very crucial final criterion for learning. And even Edward Jenner understood it, that my hypothesis explains what's going on in the data, i.e. what's going on with the milkmaid, but I need to be able to show that my hypothesis will work on a new, untested, not in the data point. So not a milkmaid, some random person, and so on and so forth. Okay, so that's just an interesting story that people will go to extremes to prove that their hypothesis is good, and you have to go to those extremes because it's not sufficient to show me that your hypothesis works on the data. Okay, so let's derive the simple perceptron learning model. Okay, and in deriving this simple perceptron learning model, we're going to, identify a hypothesis set. Okay, and then we're going to have to talk about these two things that I mentioned about a learning algorithm. You have to tell me what's the criterion by which you're going to pick a hypothesis from your hypothesis set, and then how are you actually going to do it? Okay, because you need both of those to come through for the learning model to work, to be applicable to a data set. And then at the end of the day, that just makes the learning model applicable to a data set. But is the learning model going to perform learning will come later when you test the final hypothesis and see, does it approximate F? Okay. And we have to talk about how do you do that when you don't have access to F. Okay, so as with all derivations, I find that when you're doing derivations with math and this and that and so on, it always helps to be on a board.